Excellent. So my name is Seth Sakamoto. I am with Electric Hydrogen. We're an advanced PEM electrolysis OEM. We're focused on industrial scale deployments of integrated green hydrogen solutions, focusing specifically on driving down the CapEx of those solutions. CapEx obviously is a very important part of this equation, but I'm actually going to talk about something a little bit different today, which is accelerating the deployment and development of these projects through integrated solutions like the one that Electric Hydrogen is bringing. I come from a background in the renewable energy industry. I spent about 15 years doing in the solar and energy storage space with a variety of roles from project development to project management, sales account management. So I'm familiar with all the pitfalls and challenges associated with getting projects to that critical milestone of FID. And there we go. Not unlike renewable energy projects, these industrial scale green molecule projects are massive undertakings, and they have three sort of critical pathways or work streams that you need in order to get to that FID milestone. To borrow the three-legged stool analogy that I've already seen used a few times this morning, really you need power, land, and offtake. Of course, there's other factors that need to be considered in FID for one of these projects, but fundamentally, without any of these, your project is highly unlikely to move forward. And that FID milestone is critical because these industrial scale projects are hugely capital intensive, and nearly all of them will require some form of third-party financing. Without one of these legs of the stool, your project is not likely to get past that critical milestone. And keeping in mind that all of the development dollars spent prior to that FID milestone are really at the developer's risk. And developers and project, end users who are developing their own projects are in a race against time and changing market conditions, as well as their own development budgets to deliver these projects as quickly as possible and move past that FID milestone. So the questions that developers need to answer in order to move through those work streams are, how much power do I need? How much land do I need, and where does it need to be? And what price can I offer the end product, whether that's green ammonia, e-methanol, e-methane, or just gaseous hydrogen? How do the project economics stack up in order for me to derive a project price that I can then go and contract? To complete these work streams, and sort of the traditional project approach for these is very bespoke. You're working with consultants and engineering firms to put together lots of different pieces from different vendors that are expensive and result in high degrees of uncertainty. Developers can spend months, even years, and millions of dollars in studies and realize at the end that their projects don't have the fundamentals they need to get to FID. So what are we doing differently? Well, Electric Hydrogen exists to enable critical industries to decarbonize at the industrial scale, and we want to make green hydrogen an economic inevitability. Our integrated solution unlocks the ability to advance industrial scale projects where CapEx is really a make or break challenge for these projects. We're following a successful playbook. We've done this before. The leadership of our company comes from First Solar, where they drove down the delivered cost of energy through innovations at both the component and the system level. Other leaders in the company have done that in the battery storage and semiconductor space, and now we're turning our focus to hydrogen, really running the same playbook. So what is that playbook? It is a fully integrated solution. Electric hydrogen drives down the LCOH by really revolutionizing the scale at which the industry is targeting these green hydrogen projects. This is how we get to the Earthshot goal of $1 a kilogram of hydrogen. Having a pre-engineered, factory fabricated solution that minimizes project level cost variability, project level engineering efforts, and field time, which ultimately is very expensive when it comes to the total installed cost of these projects. Because each of the modules that are part of this plant are factory fabricated, they're factory acceptance tested before they're even shipped to the field. And then the actual field time for both construction and commissioning is very short, ultimately resulting in rapid deployments and low total installed costs of projects and low LCOH. So using this approach, you're simultaneously driving down CapEx and increasing price certainty for your project at a very, very early stage. This is a block diagram showing the scope of the project. And folks who have developed these projects, we talked to quite a lot of them, will tell you that the interfaces are really the pain points for these projects, where you need to work with the interfaces with different OEMs. Each one of those interfaces represents a project-specific engineering effort and cost. It represents uncertainty and just general additional resources and time for your project development. And so we've designed a scope and an offering to really minimize those number of interfaces. Our product, the upstream battery interface is medium voltage power and potable water, and the downstream interface is your gaseous hydrogen and an effluent stream of water that doesn't get through the water purification. But everything else is within the scope of the product. So you have one partner that you're working with for power conversion, for electrolysis, for gas process, for cooling, system controls, and all of that is procured, engineered, procured, shipped to site, field assembled, and commissioned by a single partner. So really minimizing the potential for scope gap and minimizing the need for project level engineering. Now, this isn't the whole project. This facility we recognize does not stand on its own. Projects will have compression or additional purification, downstream molecule processes, but developers that we're talking to have affirmed that this equivalent scope can be 50 to 65% of the total installed CapEx for a green hydrogen project. So being able to firm up that percentage of the total cost stack very early on with minimal project-to-project cost variability is hugely valuable in being able to derive your power needs, your land needs, and your ultimate levelized cost of hydrogen that you need to go and get offtake. But just knowing the footprint, which is about 1.5 acres for 100 megawatts, and the CapEx is not the only thing that you need. You still need to figure out how much power do I need. And key to that, Electric Hydrogen has developed a suite of software, 2 different platforms actually, LCOH and LCOH Plus. So these are hosted on our website, eh2.com, and free for folks to use. You can sign up and use them. LCOH is a fantastic, simplified annual levelized cost of hydrogen calculator that will allow you to very, very quickly optimize and run sensitivities for different conditions of a hydrogen project. You can see in the chart there on the left, that's an LCOH curve that shows different CapEx. Each one of those series is a different CapEx assumption, and the LCOH impact of different capacity factors for a project. And you can use this to gauge how much effort do I need to put in to get my project from a 60 to an 80% capacity factor, or 80 to 90%. Is it worth it for the extra CapEx and effort when my LCOH is not going down that much? And then LCOH Plus is a detailed hourly model that allows you to pick a location, and it will pull the wind and solar resources from that location. You can then model what a LCOE would be for new wind and solar deployed in that location. So it's giving you the geographical ideas of where you might want to site this project. You can easily play with the mix of wind versus solar to find that optimal LCOH configuration for your project. Oversizing, how much power do you need relative to your electrolyzer capacity? And then detailed OpEx and CapEx estimates that ultimately lead to an LCOH calculation that you can see on the chart there. It'll tell you, what your average load factor and efficiency at the plant level is for your project. And this is the information that you need to then go out and source PPAs or find land to develop your own renewables for projects. And so the bottom line here is that using a integrated solution that captures well more than half the CapEx of a industrial scale green molecule project, and the innovative tools that electric hydrogen has developed to help you do very early and low cost optimization of projects, you can move your projects through the project development phase and get to FID that much faster. So I'll take any questions if anybody has any questions about the, yeah?
Great presentation. So in your concept slide, you talked about core IP for electric hydrogen is the electrolyzers and controls. I'm curious, you didn't really talk about the electrolyzers. PEM, alkaline, how many hours of operation you have in a lab, how many hours of operation you have in a field facility. Yeah. I'm just curious if you could talk a little more about that.
Yeah, good question. So it is an advanced PEM electrolyzer that electric hydrogen has developed. We've got hundreds of thousands of hours of runtime on our cells, and we're in the process of scaling. So we've got operating, we have a 1 megawatt stack that's been operating well over a year. We just commissioned a 10 megawatt project earlier this year, and then we are deploying our first commercial scale project for a customer. That's the full 100 megawatt plant. That's going to be for New Fortress Energy later on this year. That should be mechanically complete by the end of the year and producing gas first quarter of 25.
Hi.
Hi.
What is the stack size you have, and how many stacks are there in 100 megawatt?
So I know folks really want to know some of the technical details. I think one of the things I want to focus on is that we're providing the integrated solution, right? So we have 10 megawatt stacks as part of the plant, but the focus here is that we're trying to bring a complete solution where we're doing all the engineering work, not just at the stack level, but at the plant level, and all these interfaces between power electronics and stacks, for example, which is a very close coupled relationship, to make sure that you're getting the most efficient and highest value operation for the lowest possible cost. This plant, we're getting feedback is 40 to 50% less for the equivalent scope relative to a conventional sort of stick-built green hydrogen project. And a lot of that actually is also because the whole plant is outdoor rated. If we go back one more. So we don't need a building. You saw RWE presenting about the building for their project. The feedback that we've gotten from developers and operators of electrolysis projects is that buildings are exceedingly expensive and hard to permit. And so from the get-go, we've eliminated buildings from the design. The stacks are in a ventilated enclosure that has safety interlocks, so it's not an occupiable space.
Yeah, thank you very much. I also would like to dig into detail in terms of the stacks, because I think you show 16 stacks here, and how does this work then with 10 megawatt per stack?
Come by we've only got about a minute left. Come by the booth later on, and we'll get into the details about the stacks.
Thanks.
Anyone else?
Great. Thank you very much.